We'll just finish that for next time, okay? Bye. Bye. Thank you. You're welcome.
Right. Hello, everyone. Let's get this device hooked up. All right. So got that. All right. If you haven't already done so, there should be on Blackboard a Mathematica file for today's class. So go ahead and download that, and we will be using that a little bit later today, but just get that downloaded right now while I wait for a few more people to show up. It should be matrices corrected notation. And meanwhile, I am trying to figure out, I was setting up a very simple thin lens in Zmax, and for reasons that I cannot understand, I see. I was wondering why this wasn't all coming to a focus, and it's because I had multiple wavelengths in the file that I had set up. So it was not optimizing. What I had was, if you just look at one of the wavelengths, say wavelength 1, and we do a quick focus, you will notice that it doesn't quite come to a focus. And there's a very good reason why it doesn't come to a focus, because it's trying to balance wavelength 1 and wavelength 2. But I forgot that there were multiple wavelengths. And so when I asked it to, actually, it wasn't even trying to balance them. Wavelength 2 was the only wavelength that it was focusing on, because it was the only one that it was giving weight to. So once I correct that, then a quick focus should bring that wavelength into better focus. Anyway, at this point, we have 12 students plus 2 logins by me. So we're going to get started. We're going to do a few things today. We're going to start by talking about lenses that have different media on each side, because I want to take a step back and look at more complicated systems with more elements in them. And then we're going to add a few more features to what we know about lenses, stepping further beyond thin lenses, talking about the fact that they no longer have infinitesimal thickness. Then we're going to derive a very generalized thin lens equation. And once we've derived a very general thin lens equation, then we will start talking about matrix optics, which is a way to simplify calculations with many elements. Any questions before we get started? Okay. Yeah, Justin?
Can I speak with you after class?
I can't hear you. Let me adjust my volume. Okay, try again. You're muted. Justin, you had a question?
I said I would speak with you after class.
Oh, after class? Okay. All right, yeah, we can talk after class about whatever. All right. So I'm going to set up a system here where we're going to have something that's infinitely thick. And then we are going to have something of finite thickness. And then we're going to bring this into focus. And I'm going to show a little bit of the medium on the left. So, all right. Pretty simple situation. Standard biconvex lens, parallel rays, they come to a focus at the focal point. Now I'm going to put water on the right side. And, oh, actually, I'm going to do one other thing. I'm going to make this lens have different curvatures on each side. All right, now that I've done that, I've got a nice asymmetric lens. I'm going to put water here. And it should be to nobody's great surprise that the rays of light are not coming to a focus. Why? Anyone care to explain why they are not coming to a focus where they were before? Well, we put water on the right side.
Well, water has a higher index of refraction than air. So by obeying Snell's law, the refracting rays on the right side of the lens will not deviate as much and will need a farther image distance.
The only thing I would quibble with is it's not just that it has a higher index than air, but that it's closer to glass, so there's less bending. If we had given it it's not just about whether the index is high or low, but whether it's close to the other one. It's that difference in refractive index or contrast of refractive indices that changes it. Now, we could find out what the focal length is. And it looks like the focal length is well, the focal length is 59.46, more or less. Although, if we look, let's get rid of that water. It says that the effective focal length of this system is 26. And we notice that the distance from the edge of the glass to the image is 25.4. And you could say, well, you know, it's actually measured relative to the center of the lens, except that the lens has a thickness of 2 centimeters. So if the focal length were measured from the center of the lens, then it should be 26.438, but instead it's 26.010. And then some of you noticed that before, and I would just say, well, you know, it's kind of approximate. I'm pointing this out now because today we're going to develop the techniques for making sense of that. But let's go back to having water there. And we focus it. Okay, and we look at our layout, and yep, it's focused. Well, now I am going to flip the lens. And we still have water on the right, and we still have air on the left. But what we find is that when we flip around the lens, suddenly the focal point has moved. Anybody care to guess why the focal point has moved?
Sorry, what did we just adjust that led to the focal length changing?
Here, I'll change the setup so we can see both windows at once. Tile all windows. Okay, what we did was we flipped the orientation of the lens. So right now it should be focused. Yep, it's focused. Then I just turn the lens around and suddenly the rays are coming to a focus over here instead of on the right.
Well,
I mean, like we learned with our uh, sorry, I'm having a brain fart.
It's okay.
the F effective changes because of how the orientations are flipped.
Yeah, well,
Right.
that does change, but here's the weird thing. All right, I'm going to go back to when we just had air on both sides. And if I flip it, so I go 40 minus 20, it's going to probably actually shift by, some fraction of a centimeter, but it's not a substantial shift. Whereas as soon as we put water on the other side, all bets are off. All of a sudden, everything becomes asymmetric.
Right, because from that last curve of the glass to the water interface, I'm guess I definitely there's going to be a change with how the rays are refracted. Like we mentioned earlier about how the index of refraction of water and glass are very similar to each other.
Well, keep this in mind. The how much rays get deflected at a surface depends on two things. One, it depends on the ratio of refractive indices like we've been talking about. But two, it depends on how curved the surface is. And so having a highly curved glass surface in contact with water is going to give you a different amount of bending than if you have a flatter glass surface in contact with water. Now, when both sides were in contact with air, it didn't really matter. We had, quote unquote, the same refractive power at each interface. But now, the sum of the refractive powers was the same because, the more curved one has its refractive power, the less curved one has its refractive power, and we're just combining those two refractive powers. It didn't matter which one was in contact with water because neither was in contact with water. They were both in contact with the same thing. But now I can change the refractive powers of the interfaces by changing the orientation because it also affects which medium they're in contact with. And so I'm showing you this example to make sense of the result that I'm going to derive in a moment. Any questions on this before we start doing some equations?
Would this be considered a stigmatism aberration?
No, this is not an aberration. There's absolutely,
sorry.
Because, well, it's not an aberration because we are going to do paraxial theory and find that even this is something that happens even in the paraxial limit, even in the small angle approximation, thin lenses, everything close to the axis, this change in refractive index, this change in focal length still happens. So this is actually not an aberration. There is nothing going wrong. Well, I guess to say an aberration is something going wrong is to say it deviates from what we wanted. But then you could say, why is the thin lens equation what we wanted? Well, the thin lens equation is a very simple relationship, and what we call aberrations are deviations from it. But this is just a small change to the thin lens equation, and it's fully consistent with that. Other questions?
Professor, would it be the same concept as one of the problems in a problem set where we had to find out which side the light bends harder, I guess, of a Plano convex lens, but for that one, it was like a flat side and a curved side. And then when the light rays hits the curved side, it obviously bends harder, but it's kind of similar to this situation. But I guess the curved side is touching water or facing water.
So the thing about a Plano convex lens is that in the paraxial limit, it doesn't matter which way it's oriented. As much as I've been saying that in principle, if we use Snell's law exactly, there will be a change. I mean, there's definitely a bigger change in this case than in this case. There's definitely a bigger change at one interface. This one produces a smaller change, but then the second, I obviously didn't draw any of that to scale. This one produces a smaller change there, but then the second one also produces a deflection. So what am I trying to say? What I'm trying to say is that in the case on the left, if we only ask what happens at the curved interface, you're right, the case on the left produces a larger change at the curved interface. But in the case on the right, there are two changes. There's one here at the curved interface and a second change at the flat interface. And the combination of those changes is in the paraxial limit approximately the same. Right? So these two changes are approximately the same in the paraxial limit. It's only in the non-paraxial limit that they are different. Whereas if we were to compare optic axis, lens, I'm going to put H2O here, all right, and I should probably, I should try to make these two surfaces have different curvatures just to make everything more realistic. If I were to compare this case with this, if I were to compare these two cases, in each case, H2O is on the right. Even in the paraxial limit, we get different results for this combination and this combination, all right? So what do I want to say? Plano convex lenses with air on both sides, orientation only matters for aberrations. Lenses with air, lenses of whatever shape with air on one side and water on the other side, unless they're perfectly symmetric and we're doing some special case, the difference isn't just for aberrations. The difference is even for the case of paraxial rays. Other questions? Here's how important this is. I'm going to share a story that was told at an optical society meeting a few months ago. Someone from an optical engineering firm was telling stories, and these customers made him sign a non-disclosure agreement. So there's a lot he couldn't tell us about the customers. But he said that these customers were very cagey even with him. So even if he violated the agreement, there wouldn't be a whole lot for him to disclose because there's very little that they told him about the application. And he asked them a whole bunch of questions. and carefully explained refraction. And they built whatever it is that he needed. And the only thing he mentioned to us is that somewhere in this optical instrument, refraction was involved. That's all he said. And they build the device, they give it to the customers, and the customers say, oh, that looks beautiful. I can't wait to get it in the water. And at no point had the customers mentioned previously that this thing was going to be operating underwater. And can you see why that would be a problem if you have a lens or even a window at which refraction is happening and you're working underwater? Hopefully. Let's do some theory here. So we are going to consider initially just one curved interface. And we've got an object point at a distance S1. And all the rays are going to go to an image point at a distance SG, because it's inside the glass. And this medium on the left has an index N1, and the glass has an index NG. And we are going to have to make it so that all of the paths take the same time. This path on axis will take the same time as the off axis path. So let's see here. Time for the on axis path. Well, that's going to be S1 over C over N1 plus SG over C over NG, which is N1 S1 plus NG SG over C. Then we look at the off-axis path. Well, it hits a distance y off-axis, and this distance on axis, this extra little distance on axis, is x. So if I try to measure the length of this using the Pythagorean theorem, that's going to be the square root of y squared plus s1 plus x squared. And this is going to be the square root of y squared plus sg minus x squared. So the off-axis time will be equal to n1 square root of s1 plus x squared plus y squared plus ng square root of sg minus x squared plus y squared all over c. Any questions so far? Okay. Well, I'm going to get rid of the c's. They just cancel out. We equate these times. Cancel the c's. N1 S1 plus NG SG. And then I'm also going to take advantage of the fact that x is tiny. So x squared is really tiny. And I'm going to write this as N1 S1 squared plus 2S1 x plus x squared, which gets crossed out, plus y squared plus ng square root of sg squared minus 2sgx plus x squared, which we can again cross out, plus y squared. Any questions? Well, then what we're going to do is we're going to factor out the big number under each square root. The big number under each square root is s. It's going to be n1 s1 square root of 1 plus 2s1 x plus y squared over s1 squared plus ng square, ng sg square root of 1 plus negative 2 sgx plus y squared over sg squared. Any questions on that? Well, now I've got the square root of 1 plus a comparatively small quantity, because however big x and y are, s1 is much larger. So what would you think we're going to do next? Small quantities. What do physicists like to do when we have a messy function of 1 plus a small quantity?
Binomial theorem.
What theorem?
Is it binomial theorem?
Binomial theorem or a Taylor series. So we're going to say that 1 plus u to the n is roughly 1 plus n u. And in this case, n is 1/2 and u is this. And so we're left with n1 s1 times 1 plus 2s1x plus y squared over 2s1 squared plus ngsg times 1 plus negative 2sgx plus y squared over 2sg squared. And that's equal to n1 s1 plus ng sg. All right. I see something that could cancel, because if I multiply the n1 s1 by the 1 in here and the ngsg by the 1 in there, the first term, you're going to get two terms that exactly cancel out these terms. So I'm just going to cancel the ones there and all of this. And what I'm left with is n1 s1 squared x, 2n1 s1 squared x over 2s1 squared plus 2n1 s1 y squared. Sorry, that's not a 2. Plus n1 s1 y squared over 2 s1 squared plus minus 2 ng sg squared x over 2sg squared plus ng sg y squared over 2sg squared, and all of that is equal to 0. Now we tidy up what we can, cancel some 2's and s's, cancel some 2's and s's, and cancel one factor there. And I will rewrite all of this as n1x plus n1 over 2s1 y squared minus ngx plus ng over 2sg y squared equals 0, which doesn't yet look like much. Well, let me make one more manipulation before we do what we did a few weeks ago and take a second derivative. N1 over S1 times y squared over 2 plus NG over SG times y squared over 2 equals x times NG minus N1. And then we take d squared by dy squared. Usually we take second derivatives with respect to x, but that's when we have a curve that's either sloping, that's either bulging up, opening down, or bulging down, opening up along the horizontal axis. Here, our bulges and openings are to the left and right. So let's see here. Second derivative of y squared. Well, first derivative of y squared is 2y, which cancels out the 1/2. And then the second derivative is just 2. It's the derivative of y with respect to y. So we get n1 over s1 plus ng over sg equals ng minus 1, sorry, ng minus n1 d squared x by dy squared. Now, does anybody remember what that second derivative was? It was on the first practice assignment. What is the physical meaning of the second derivative?
Radius of curvature.
Yep, it is the radius of curvature. Thank you. So it's ng minus n1 over r1. Okay, we've got something that looks kind of like the thin lens equation, except that instead of just 1 over s, we've got n over s. Any questions on this?
Is this not the lens maker's formula?
It's half of the lens maker's formula.
Oh, okay.
Now, so far we just sent the light into the glass. But then I could immediately put a second surface there, N1, NG, N2. And all of those rays that were coming to a focus over there, well, we'll say that what we've got is a virtual object at a distance S1 equal, it's not really S1, but we'll just say that at the distance S object equals minus SG. And you might say, well, shouldn't it be SG minus the lens thickness? For now, for the remainder of the 5 o'clock hour, maybe not even the full 5 o'clock hour, we're still dealing with thin lenses. We're going to relax that assumption by the end. But if we just leave that out, we've got an object at a distance minus SG. Right? And so we could go through all of the same steps that we did again with just the following changes. 1, replace S1 with minus SG. Replace N1 with SG. Meanwhile, everywhere that we had SG before, replace SG with S2 and replace NG with N2. So if we change a few names, we're solving the exact same problem that we just solved. And we would get, oh, and there's one more thing. No, actually, we don't need to worry about that yet. So if we make all of those changes, we get that minus NG over SG plus N2 over S2 equals N2 minus NG over R2, or NG minus N2 over negative R2. And that is the second half of the lensmaker's equation. Then we take this equation and this equation, we could just add them. When we add, these things here will cancel. We'll keep this, we'll keep that, we'll keep this, we'll keep that. So on the left side, we get N1 over S1 plus N2 over S2 equals NG minus N1 over R1 plus NG minus N2 over negative R2. Any questions? You might think we've generalized the thin lens equation, but all we've really assumed is that we've got some Cartesian ovals designed to take something from here to there. We haven't proved that these Cartesian ovals will work for any other pair of points. We're going to, but we haven't proved it yet. And before we prove it, I want to introduce just a couple more generalizations on the thin lens equation. Nobody has any questions whatsoever. Just to connect this with what we've been doing though, even though we haven't really proved that we can use this for any S1 and S2 that we want, we're going to prove that. Given that we're going to prove that, let's just think about the implications. What if S1 is infinity? Okay, if S1 is infinity, then N2 over S2, NG minus N1 over R1 plus NG minus N2 over negative R2. And so I could divide both sides by N2. And I would get that 1 over S2 is all of this. So far, so good. You think, okay, so S2 equals 1 over all that. Well, then somebody says, you know what? I'm going to swap around the radii. I'm not going to swap the media. I've still got air on one side and water on the other side, but I'm going to swap the curvatures. Okay. So we swap the curvatures. And we still say S1 is infinity. We're still sending in our rays parallel to the axis from the left, just like I was doing in Zmax the whole time. Well, now 1 over S2 is equal to NG minus N1 over, if I'm swapping the curvatures, I'm also multiplying by -1. NG minus N1 over negative R2 N2 plus NG minus N2 over N2 R1. No, I should be swapping the signs. No, I was right the first time. Anyway, leaving aside the sign errors that I know I'm going to screw up, are these two expressions the same? Is S2 the same in both cases?
No.
Nope, because before I had NG minus N1 over, let's just plug in some numbers. Let's say that NG is 1.5, N1 is 1, N2 is 1.33, and I don't know, R1 will be 20 centimeters, and R2 will be minus 10 centimeters. So that the lens looks something like that, more bulging on the right. Case 1. So 1 over S2 is 1.5 minus 1 over 1.33 times whatever R1 was, 20 centimeters. Oops, 1.33 times, well, let's see, there's a minus sign, times 10 centimeters. So we've got 0.5 over 20 times 1.33, well, 20 times 1 is 20. 2 times 0.33 is 0.66, multiplied by 10, and we got 6.6, so 26.6 centimeters plus 0.17 over 13.3 centimeters. Somebody can run that through a calculator. Flip. R1 should be 10 centimeters because now it's bulging like that. R2 is negative 20 centimeters. 1 over S2 is 0.5 over 1.33 times 20. No, 1.33 times 10 plus 0.17 over 1.33 times 20. So we finally get 0.5 over 13.3 centimeters plus 0.17 over 26.6 centimeters. Even without running it through a calculator, I can just see that these are different numbers. Somebody must have a question. Anyone? Nobody has a question? Either this is completely confusing you or it's perfectly easy. Those are the two reasons why no one would ask questions. But to be fair, in the first case, you really should ask a question. Brain dead. I see in the chat. Nine to 5 kills you. Okay. All right. What I want you to take away is that normally, if we didn't have to worry about water on one side, air on the wire, you just say, well, there's usually more bending at the more curved side. But how much bending the more curved side produces now depends on, well, is that more curved side also facing air, in which case glass is going to give you a whole lot of bending, or water, in which case the glass doesn't give as much bending, but if it's curved enough, there might still be a lot. Okay, So the effect of that highly curved surface could be partially canceled out by putting it in contact with water instead of air. And that's why you get a different result on the two sides. But here's something else to notice. What if we had flipped it, sent the light in from the other side? So we got N1 over S1 plus N2 over S2 equals this whole combination of indices and curvatures. All right, this is just some number. And we know that if S1 is infinity, S2 is equal to N2 over the right side. But what if S2 was infinity? So you imagine that we're sending in light the other way. We send in our rays of light like that. Then we could calculate S1. S1 would be N1 over the right side of the equation. So it'd be N1 over all of this mess here. That should again point out the fact that we get different focal distances. Okay. Before I prove that the thin lens equation holds true in this case still, I want to point out one other complication. I've been showing you occasionally lens files, and I've been saying that you'll often see people put several lenses together. And the reason why we put several lenses together is because maybe we want to partially cancel out some aberrations. So we have this basic question. What do we use as a focal point? And what do we use, and where were we measuring all of the S's with respect to? Well, let's just start by observing that we could still, via experiment, find a right focal point. All right. The right focal point may be a mess to figure out calculation-wise, but one way or another, you send in rays and they would start going to wherever they go, and then maybe they would spread out, and they would spread out. And in the end, they all come together back here. And however tedious it might be to calculate that, we could say, well, this is definitely our right focal plane. Any questions on that idea? We could do the same thing for rays coming from the other side. We could send them in. We'll ignore the fact that I've drawn them so far off axis that we're going to undoubtedly deal with some terrible aberrations here if this were a realistic lens, but it's not. If we continued them over here, they would probably go like that, and then they would come to a focus way back there, and we would say that this is our left focal plane. How would we measure a focal length? Any ideas on how to get a focal length? How did we define a focal length a few weeks ago when I worked out this formula for the simple case of two lenses separated by a distance d?
It was the inverse of the focal lenses added together minus d over their product.
Yep, but what was the physical assumption that I used in order to derive that? What was the physical idea that went into that derivation?
Oh,
Anyone else?
Is it Paraxial Rays?
There were paraxial rays. And what did we do with these paraxial rays? What was it that we imagined doing? We sent some paraxial rays into this. All of those rays,
they're parallel.
they were parallel to each other. That's right. And then what did we try to figure out?
Y equals F tan theta?
Yep, we looked to see where they all came to a focus over here. And wherever they came to a focus, we said that that is
Or
y equals
F effective.
Yep, the effective focal length. So we could do an experiment where we just send in a whole bunch of parallel rays, and they're going to do God only knows what in there. But in the end, they're going to come to a focus right there. And that would be y equals F tan theta. And there would be some ray that made it to there, traveling parallel to the optic axis. And it might not have, I should probably undo that drawing because there's no guarantee that it went through the center of that lens. But there's going to be some ray that just happened to make it there, going parallel to the optic axis, going in the same direction, parallel to its original direction. I don't know what I'm saying. Parallel to its original direction, right? There's going to be one of them because there's some that are going to be coming from way down there, making a much steeper angle, and some coming from up here, making a shallower angle. So one of them is going to make the same angle that they originally made. And we can ask an interesting question. What point on the axis did that ray come from? And you might say, well, what if it didn't come from a point on the axis? What if it was like this case? Okay, so, it never actually came from a point on the axis. It was just going, but it never went, it never actually came from the axis. It came from the lens. And so it was doing something else when it was inside the lens. Well, it's still behaving as though it came from that point there. So there is a point on the right that there's a pair of points, one on the right, one on the left, that have a very special property. If I aim a ray at this point on the axis, on the right, it will be going at the same angle that it came in at. And it'll either come from this point on the axis or at least act like it came from that point. So there's this very special pair of points called nodal points. And nodal points have the property that a ray aimed at left nodal point comes out of the right nodal point traveling in the same direction. Questions on that definition? So we've got our focal points. Our focal points are the points that rays eventually make their way to if they come in parallel to the axis, right? You send in rays parallel to the axis. They're going to do all sorts of things as they bounce around. Well, not really bounce, but you know what I mean, go up and down, traveling between these lenses. But in the end, they all make their way to a focal point. That is the definition. Whether you do a simulation in Zmax or a matrix calculation, or you do an experiment in the lab, that's how you find a focal point. You send in rays parallel to the axis and say, where did the rays go? Nodal points. You send in a ray pointed at that nodal point, and when it comes out on the other side, that's the point that it's traveling from at the same angle that it came in at. And you can use these to figure out where you're going to measure your S2 and your S1. And let me give you a concrete example of that. I said last class that we would sometimes have a pair of lenses with equal and opposite focal lengths. Plus F minus F. Why? What was the application? What was the situation that we talked about these being useful in? Does anybody remember? I said that they automatically correct for a special aberration.
A field of curvature.
Yep. They don't have any field curvature, which means that if we send in rays, whatever those rays do, the focal plane on the other side will be a plane. If we didn't correct for it, this could be your focal plane. Flat focal plane. 1 over r focal plane is the sum of 1 over n f. If these two lenses are made out of the same glass and have equal and opposite focal lengths, then we don't have any field curvature. So let's deal with that situation. I want to make things concrete with that situation. So I'm going to make this as special as possible. I'm going to have plus F, and I'm going to put them separated by 1, 2, 3, 4, 5. I'm going to put the other lens right there, minus F. I'm going to say that their separation is F. Okay, how are we going to figure out where the right focal point is?
Use the formula you just wrote down on the top right.
Well, that's the focal length. All that says is that wherever these rays are going to come to a focus, if I send in some parallel rays, some rays parallel to the axis, they're going to come to a focus at a distance y equals f tan theta off axis. So that'll tell us how far off axis they'll come to a focus. But where along the axis? Is it going to be here, 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 somewhere else? How are we going to figure that out? Let's just trace and see what happens. They hit the first lens. Where do they go?
They converge.
To right there. Now, if we pretend that everything's actually paraxial, they are hitting a surface that looks vertical. They pass through this vertical surface, through another vertical surface. What do they do when they come out? Don't overcomplicate it.
Diverge.
From that point. So look, here's our right focal point. And you're thinking, okay, is the right focal point always in the last lens? Let's send in some rays from the right. What does that first lens do with rays coming in parallel to the optic axis? What does a negative or a concave lens do with rays that are coming in parallel to the optic axis? Does it focus them to a point?
No.
So what does it have to do instead?
Diverge them.
From where?
So you're gonna first, the way that I would do it is draw the virtual image, which does converge, right, to the right side of the lens, and then
Making
draw lines outward that diverge from the optical axis outward toward the lens.
So they diverge from the focal point.
Right. And then you draw that through the lens outward.
Okay, they diverge from about there. Right, they diverge from one focal length back. So let's see here. This distance is F. To get, they diverge from F behind the lens. And they go another distance F. Looks to me like they come from a point 2F behind the lens. So if I've got, what does this convex lens think? Does it know that there's a virtual lens? Does it know that there's a virtual object there?
No.
Does it know that there's a concave lens there?
No.
The only thing it knows is that there are rays coming from here. So someone other than Justin, I want to hear from the rest of you. If an object is 2 focal lengths away from a lens, where does the image form? I know it's been a long week, but come on, thin lens equation. The object was 2 focal lengths away from the lens. Someone other than my 2 usual suspects, Justin and Leona. I always hear from those 2. I like hearing from them, but they aren't the only ones paying tuition here, so. Come on, S1 is 2F, what's S2? I'll just make this awkward. I'll just sit here. Someone must say.
S2 equals 2F.
Yes, thank you, Kenneth.
I was doing calculation. That's why I was quiet.
So it looks like the left focal point is there. Now, that's where the left focal point is. Where do you think the nodal points are? Sorry, it's 2F. The nodal points are just one focal length away from the focal points. So it looks to me like we've got a nodal point and a nodal point. So we could use the thin lens equation as long as we measured S1 from here and S2 from there. The thin lens equation would work. 1 over S1 plus 1 over S2 equals 1 over the effective focal length. And I'm going to prove that, but everyone's brains are fried. So let's take a 10-minute break and then I will prove that. So I assume you got my messages about the alumni career panel tomorrow.
Yes.
Any questions about it? I hope I see many of you there tomorrow. We're going to have two people working in optics. One is an engineer and the other in technical sales.
What's an
And,
associate developer engineer? Like, is that software? Is that hardware?
the one at UCI?
Yeah.
He's basically working in the stock room, helping them with stuff for the labs. So he designs labs and demos and things like that.
Ah, gotcha.
Then we've got an optical engineer at Northrop and a laser sales engineer at Hubner Photonics. All right. So let's get back to generalizing the thin lens equation. So we are going to make a few assumptions. We're going to assume that we have here a nodal plane. And-
Professor, you're not sharing your screen.
Oh, okay. Thank you. All right, so we've got a nodal plane. We've got a right nodal plane. And we've got an object point here at a distance that I am going to call S sub A to distinguish it from the other S1, and another object point at a distance S sub B. And then we've got, these are the objects that we designed for. We designed a whole bunch of Cartesian ovals to work for these. Then we've got some off-axis point here, some off-axis object point called a distance S1 from the nodal plane. And we're going to try to figure out where it forms an image. Now, let's see, we know two things here. We're just making two assumptions. One is that a ray that goes through this point on the left will go through this point on the right. So we make that assumption. And then we're going to assume that something that goes through the nodal point, I actually forgot to add one fact. This has a refractive index N2. That something that goes through the nodal point, if the left and right media have the same refractive index, then they will, then the ray coming out of the nodal point will make the same angle. But if they have different refractive indices, then the ray going through the nodal point will make a different angle given by this relationship, Snell's law. Theta 1, theta 2. And we're going to say that N1 sine theta 1 equals N2 sine theta 2. So if you aim something at the nodal point on the left, it will come out through the nodal point on the right, and the angle that it makes from the nodal point on the right will be given by Snell's law. Any questions so far? Y1, Y2, and then this will be S1 minus SA, and we'll call this distance R. We'll call this distance R. That's the other thing I forgot to mention, that when they hit this nodal plane or principal plane, that they make the same height when they come out on the other side. All right, so now we just have to do some trig, and we know that this distance is SB, and this distance is S2. And we know that this is SB minus S2. All right, what does all of that mean? How do we put it all together? Well, let's just start writing down. We've got a bunch of complicated diagrams. Let's just start writing down things that we know. Here's a pair of congruent triangles. Sorry, here's a pair of similar triangles. So y1 over s1 minus sa equals r over sa. We also know that y2 over, that looks too much like a 1/2, y2 over sb minus s2 equals r over sb. So hey, we can eliminate the r's. That is encouraging. R equals SA y1 for S1 minus SA. And it's also equal to SB y2 over SB minus S2. Now it would look like we're almost done here, except that we've got this y1 and y2 to eliminate. Well, let's see here. Tan theta 1 is equal to y1 over s1. And we know that tan theta 2 is y2 over s2. So, is there any way to rewrite these, to relate theta 1 to theta 2?
Can you write y2 in terms of y1?
Well, let's see here. I could say that y2 over y1. I could say I could start with this. y2 equals s2 tan theta 2, and y1 equals s1 tan theta 1. So y2 over y1 would be s2 over s1 tan theta 2 over tan theta 1. Okay, but we've still got this ratio of trig functions of angles. How could we get rid of that?
Could we apply approximations?
Yep, we're doing paraxial optics here. So if we're doing paraxial optics, what do we get to assume?
That if the angles are small, then theta, tangent of theta 2 is just the angle itself.
Yep, and it's also equal to sine theta 2. So I could say that y2 over y1 equals s2 over s1 sine theta 2 over sine theta 1, which is s2 over s1. And let's see, you have to work on the ratio of the sines. If I divide both sides by sine theta 1 and divide both sides by n2, I get n1 over n2 sine theta 2 over sine theta 1. Okay. So I could put all this together and I could say that y2 is equal to y1 s2, because this is equal to that. Y2 is y1 s2 n1 over s1 n2. And I know that looks like a bloody god awful mess, but then I could put that back into there. And I get that SA y1 over s1 minus SA equals SB y1 s2 n1 over s1 n2. And again, I know it looks like a bloody god awful mess, but we're about to do some simplifying. Cancel the y1s. Let's multiply both sides by that so that we get S1, N2, S. Actually, no. Let's flip both sides. S1 minus SA over SA equals SB minus S2 over SB S2 N1 S1 N2 up there, because S1 N2 was in this denominator. When we flip it, it goes into the numerator. This was in the numerator, now it's in the denominator. And then I'm going to start dividing by some S's. I'm going to divide both sides by S1. I'm going to multiply both sides by N1. So I get N1 over S1 times S1 over SA minus 1, because SA over SA equals, see, I multiply both sides by N1 and divided by S1. I'm left with N2 over S2 here times SB over S2 minus 1. I feel like I did something wrong here, but let's just keep going. N1 over SA minus N1 over S1 equals
When you have the -1, shouldn't it be S2 over SB? Or a 1 over SB? Because when you split it, there's no SB
Right.
with S2.
Yeah, okay, let's go back and redo this side. So we're going to get, I divided both sides by S1 and N2, so I just have to deal with all of this. So that should be, you're right, N2 over S2 minus, because the SBs there canceled, the S2s would cancel there, minus N2 over SB. Okay, so I pull all this together and I get, now I could move that and move that. Now I get N1 over SA plus N2 over SB equals N1 over S1 plus N2 over S2. And all of this here, that was equal to NG minus N1 over R1 plus NG minus N2 over negative R2. And so we have derived the thin lens equation. Again, any questions? That's about as far as we're going to go with using the thin lens equation. It was already pretty confusing up here when I was dealing with these two lenses, trying to define focal planes and nodal planes and everything, and deal with the fact that I've got rays traveling through two lenses. If I wanted to trace rays through multiple lenses, just using a thin lens equation each time, it would get tedious. Now, most of the time, if we need to trace rays through several lenses, as soon as we care about non-paraxial rays, we go into Zmax. But there are times when we want to get exact formulas. And there is a way to get exact formulas, which Zmax will not give you, by using matrices.
I wanted to ask really quick.
Yeah.
If when we took the tangent, we did, or when we saw the square root, we took a binomial expansion. Is it totally unwieldy to take terms of higher order n squared and above?
You absolutely could do that, and that would give you aberration theory. But the problem is that as soon as you took into account the thickness of the lens, the aberration theory would get really hairy. But yes, using the higher order terms is exactly how people derive third order aberration.
That's kind of what I wanted to go into. Okay, so yeah, so that's what they're talking about. And you said there's like they're only odd numbered. Is that right?
There should only be odd numbered terms if you do it right.
Okay.
Because a ray, if I flip everything around, it's because of the symmetry. If I flip everything around, the ray should do the opposite. Now, as soon as you get cases that no longer have that axial symmetry, all bets are off. Then you can get even order aberrations. And with some of the stuff that people are doing nowadays with freeform optics for like head displays and stuff, that stuff might matter.
Interesting. Okay, thank you.
You're welcome. Okay, so if I want to deal with a whole bunch of lenses, then we need to, express things for rays of light in terms of linear equations. And there are three basic things that a ray of light can do. A ray of light can travel through empty space or free space. A ray of light can refract at a flat surface, and a ray of light can refract at a curved surface. And as long as we're dealing with axisymmetric problems, there are just two things that we need to know about a ray of light. We need to know how far off axis it currently is, and we need to know what angle it's making. I'll call this Y1 and theta 1. And we will deal for now with translation through a distance S. It's going from left to right through a distance S. When it gets over here, it's at a height y2. And it's making an angle theta 2. Well, theta 2 is pretty easy. Theta 2 is just equal to theta 1 because it's traveling freely through a medium. It hasn't encountered any inhomogeneities. It hasn't refracted. It hasn't done anything that would change its direction. So theta 2 is theta 1, but I'm going to write it a little bit more pedantically because it's going to matter when we try to express this with matrices. 1 times theta 1 plus 0 times y1. And y2, well, let's see, we could do our trigonometry. This would be delta y. And because that's how much its height has increased. Delta y over s would be tan theta 1. So delta y is s tan theta 1, and y2 would hence be y1 plus delta y, or y1 plus s tan theta 1. Now I'm saying that I want to do things with matrices, and matrices are usually used to express linear relationships. Tan theta is not a linear function of theta, but what can we say? What is the approximation we can make?
That's approximately sine theta.
Or approximately theta. So y2 is 1 times y1 plus s times theta 1. And what people do to express these relationships is they represent the ray with a vector. And there are at least 3 different notations. You've got theta 2, y2, or y2 theta 2, or, and here I admit I'm deviating from the book, some people will write n2 theta 2, y2. The reason why they write n theta instead of theta is because n theta or n sine theta doesn't change at a vertical surface. And so they're like, hey, then refraction at a flat interface doesn't change anything. Okay, it's still a very tedious notation to work in. I'll deal with this one because I want to include changes rather than treating things as trivial. It makes things so easy that you wind up forgetting a whole bunch of places where you need to then divide out that n. I don't want to divide out the n because I'm going to forget to divide out the n. So we'll stick with this, and we get the theta 2 y2 is equal to 1 times theta 1 plus 0 times y1, and s times theta 1 plus 1 times y1. Well, let's see, that looks a lot like multiplying a matrix by a vector. So I'll write that as 1, 0, s1 acting on theta 1, y1. Any questions? Hearing none, I'll go on. There's another easy matrix, and then we get into some hard matrices. Refraction. So here we've got an interface. Here we've got our axis, n1, n2. A ray comes along and it hits it here, and then it changes direction. So here's theta 1, here's theta 2. We know that n1 theta 1 equals n2 theta 2. So by Snell's law, theta 2 has got to be n1 over n2 times theta 1. And it doesn't depend on y. So I'm going to write that as 0 times y1. Because when we have to translate from linear equations to matrix elements, people get confused, like, but the equation doesn't have this. And I say, yeah, you're right. That's not in the equation, which is the equivalent. If this variable doesn't show up in the equation, that's the equivalent of multiplying the variable by 0. And that way we have a 0 in the matrix. Sounded way more movie-like than I intended. What's y2? Does the height of the ray change when it's passing that infinitesimal distance across the barrier, across the interface?
Not really, no.
No, it was up here on the left side, still up there on the right side. So y2 equals y1, or I can write it as 0 times theta 1 plus 1 times y1. So what I'm left with is theta 2 y2 equals n1 over n2 theta 1 plus 0 y1, 0 times theta 1 plus 1 times y1, or n1 over n2 0, 0, 1, theta 2, sorry, theta 1, my bad, y1. Any questions? Then let's deal with a lens, a thin lens, and then we'll get to curved surfaces and thick lenses. Okay. This is the difficult part. We need to figure out what happens. To do an arbitrary ray is very difficult. And we've got some arbitrary ray that comes in at a distance y1 off axis. It's making an angle theta 1, and it's going to come out making whatever angle. So let's deal with different cases. We've got that theta 2 y2 equals a, b, c, d times theta 1 y1, or theta 2 equals a theta 1 plus b y1, and y2 is equal to c theta 1 plus d y1. Well, assuming that the lens is very, very thin, does y change passing through the lens?
No.
Nope. So these are easy. C is 0 and D is 1. But A and B are trickier. You could think of A as saying, if y was 0, okay, if we sent in something, if we had a case where y was 0, then theta 2 cannot possibly depend on y1. And that's not even thinking about right now the physics of it, about a ray going through the, you might be thinking, well, of course it depends on y1. But I'm saying that the symbol y would not show up anywhere in there. Theta 2 would just depend in some way on theta 1. Right? If it was 0, if we had a 0 y, then our new column vector would only have theta 1 in it. And it would have to be this. It would be theta 2 equals theta 1, or A equals 1. Think of each coefficient. Forget even about matrix optics for a moment. Think of any coefficient of a matrix as saying, how does this output variable depend on this input variable when all of the other input variables are 0? Okay, because that's all that a matrix really is. A matrix acts on a vector, and so you've got a vector of, oops, that was like that, column vector of outputs is equal to a matrix acting on a column vector of inputs. That's all that a matrix does. And each element of the matrix is saying, if we take this input in isolation, what could we say about an output, right? Each element is just a coefficient that relates an output to an input. So for this case, if I want to just deal with how things depend on y and not worry about theta, then let's just say that theta is 0. What would that ray of light do physically?
It would go through the focal point.
Yep. So make this angle theta 2. And y hasn't changed, at least initially. Tan theta 2 is minus y1 over f. Which means that theta 2, in this case, if theta 1 is 0, we're just looking at the relationship between theta 2 and y1, it would be minus 1 over f times y1. And conversely, if y1 were 0, theta 2 would just be equal to theta 1. So theta 2 is equal to c times y1, sorry, c times theta. Theta 2 is equal to a theta 1 plus b y1. And this a is saying, if we can ignore y1 is 0, what is the relationship between theta 2 and theta 1? Well, it's just 1. And if b is 0, and if theta 1 is 0, b is telling you the relationship between theta 2 and y1, and that's minus 1 over f. So theta 2, y2 for a lens is 1 minus 1 over f, 0, 1, acting on theta 1, y1. Any questions so far?
I guess I'm just confused because like on page 9 at the bottom, you see it says theta 2 equals negative 1 over f times y1. And then like the next equation kind of contradicts, right? Because in that first equation, a looks to equal 0, but then the first equation on page 10 is a equals 1.
Oh, if we take it,
I'm like, where am I getting lost? Like, what am I missing?
This is to each coefficient. The way you find each coefficient is by taking a case in isolation.
I see. So the first one is then a special case of theta 1 equals, okay. I
Yeah.
see.
This is the general equation.
Right, okay.
This is a special case. And this is also a special case. And because everything's linear, you can treat things as sums of other cases. You don't have to worry about.
Right, I see what you're doing now. That just confused me because I would have just done it right out of the bat like this way and not doing the special cases, but now I see why you wanted to show that.
So in the last minute, we're gonna have to continue with this next week. In the last minute, if we had a ray of light going from, say, this point to there, we had a bunch of rays all doing that, starting at Y1, making their way to Y2. Well, the first thing we would have to do is we would take theta 1, Y1, and we would multiply it by a translation matrix. 1, 0, S1, 1. First thing we have to do is translate it. The next thing we'd have to do is we'd have to send it through a lens. And then the next thing we'd have to do is send it a distance S2. 1, 0, S2, 1. And I know that seems counterintuitive, that the first thing you do is on the right, and then the next thing you do is 1 over to the left, and then the next thing you do after that is even further to the left. But this is not like the English alphabet where you write from left to right. This is matrix algebra where the thing that's right up against, the thing that's to the right is right up against the vector, and it's the first thing that acts on the vector. And the next thing that acts on the vector is to the left. So it's a little bit like reading things in Hebrew or Arabic or Farsi, in languages where you write from right to left instead of left to right. But it's just a matter of, rather than trying to think, wait, does physics do left or right? It's not about that. It's about what is closest to the vector. The first physical process is the one that's closest to the vector. The next physical process is the one that's a little bit further from the vector. That's all we have time for today. I'm not going to keep you any longer. We will continue with this next week. Have a good day.
Dr. Small,
Yeah.
I had a quick question about tomorrow's panel. Would you happen to know if any of those alumni are also graduate students?
One of them, I believe, is going to grad school part-time at the moment. And I think another one got a master's a long time ago.
Oh, okay. All right, I'll try asking questions then. Thank you.
One thing you should know,
Yeah.
one of the questions I will ask all of them is, what kind of continuing education have you pursued since leaving college? That's one thing all of them will be talking about.
I see. Yeah, because I definitely want to see if like pursuing grad school part-time while working is, I don't know,
Feasible?
not, I guess feasible, and just like how it is, I guess, and how acceptable I guess it is to for employers.
Well, I believe that one of them is going to be taking advantage of employee tuition benefits for that. The one at Northrop, I'm pretty sure, is doing that because the aerospace contractors generally love sending their employees to grad school, and that's one of their big selling points is the tuition benefit.
Right. Okay, that sounds
A lot
good
of
then.
tech companies will pay tuition too.
I think JPL pays tuition as well.
Yeah, I wouldn't be surprised. Okay, I'll see you tomorrow then.
All right.
Thank you.
Bye.
I had a question about the last project.
Okay.
I got a pretty bad grade. I got 20 out of 100, and I think I know what went wrong. On the feedback.
Wait, did I
from my
give you
screen,
20 or 80? I thought I took off 20 and gave you 80.
Yeah, he gave me 20, but I think I
Oh,
understand what
well, then okay. Yeah.
80 is way, that's more what I expected. Okay, because
Yeah, okay.
I was like, oh man, that's really,
By the way, I just
wow.
realized we're talking
I understand
about
what
the
I did.
grade.
I did the weight, it's the weighting. I think I did wrong. The second ray, I wanted to show 2 so I could show you the magnification was indeed 4. But by doing that, I introduced a second target and thereby another weighted ray. And so it threw off the focusing. And so that's why when you look at like my polynomial, it's not exactly 3. In fact, it started to increase towards 3 as we increase the yeah. Anyways,
I meant to
and
give you
it's funny.
a B. I meant to give you a B because it was a good report and you made
Okay.
a simple mistake. I am so sorry about that.
No, that's totally cool. I also just wanted to make sure. Okay, cool. That makes sense. Alrighty, because I thought really what I thought that meant was that I did something like even worse. Like I thought it was just that.
No,
okay.
no.
All right.
No. What
Cool.
went through my mind is 20 off, and then the number 20 went to my fingers instead of 80.
I appreciate it. Thank you so much, and
No
I'll see you
problem.
tomorrow.
All right, bye.
Bye.
Juan, you wanted to ask a question? Juan? All right, I am ending this.